And I believe we hit the hour mark, so I can start out. I will first, of course, give some more people the time to join. So hi, everyone. I'm Niels, and welcome to this session on securing the software supply chain here at NDC London. I hope you're enjoying the conference so far. I did, let's say, talk about this topic several times, and I think like with the things that happened over the last couple of weeks, there were a couple of nice new topics that I added to this version of this supply chain talk. Of course, probably you've all heard about SolarWinds and what happened with their supply chain and so on. We're going to mostly focus on supply chain as a whole and go throughout different types of risks that we're facing when we're developing software. That should be the main goal. First, it's always good to politely introduce yourself. And that's the first slide I'm going to show you. So my name is Niels Tanis, and I work as a security researcher for Veracode. I got a background in .NET development, and I've been doing security consultancy. And currently, I'm like combining all of that like background into a single role when I'm mostly working on our static analysis that we offer as Veracode, so static analysis of .NET applications. It's a lot of fun. I really enjoy it because I still keep to do a lot of development and focus on things that are like problems for our customers, and of course talk to you about the problems that we're facing and the things that we need to do. If you're interested to talk more about Veracode, come see me afterwards, because today's topic is going to be the software supply chain and the ways that these types of supply chains can be attacked. And we're going to implicitly answer the question during this session is like, how secure is your .NET application? So if you've got questions, feel free to drop them in the chat on WebEx. I'm completely fine with that. You can also just use the Slack channel. Let me open up track number 6 in order to make sure that I see it. And of course, always an email and all the other like communication handles will be mentioned at the end. I'm also referring a lot to articles that are published that you can find on the internet. So at the end, I will have a repo that contains the demo that I'm going to show you in combination with all the slides. And there also will be notes in those slides that will contain the links to the articles that I've used. So if you look at development and how it has changed, right? So myself, I started out development in the early 2000s with .NET, and of course, the things that we do at that stage was mostly writing monolithic applications that were a single install at one customer that would, let's say, automate a specific process. That was the goal. If you would compare it to the way that software gets developed nowadays, is of course, there's a lot more continuously done, like deployments, integrations, code is being changed. The companies will probably deploy several times a day, right? And the whole build process, so the whole supply chain of how the software is being created, so from starting source code to the end product that will be deployed, has become a lot more complex, and there's a lot more moving parts. And with that, of course, also comes a lot more security risk. So that's in stretch the topic that we're going to cover, and I'm going to use the following agenda for that. First, we need to touch on some hacker history and some evolution of how hacking has changed and why we need to focus on our supply chain right now. Then, of course, we need to have a definition of supply chain, like what is it? We're going to take a .NET development application, like a development of a .NET application as an example, and then we're going to go through the different stages and see what type of risks that we're facing. And then at the end, of course, I think maybe the most important part of this presentation would be like, hey, how can we take the right countermeasures for securing our supply chain and for having a better eye on when stuff gets compromised, because it's hard. And I technically would say, like, is there a way for us to fully like fix this problem? That's a big no, right? This will always be around, but you need to make sure you make the right decisions and also have the right countermeasures in a laid way in place. But that's something that we're going to cover throughout the talk. As I said, Q&A can be answered right away. Completely fine with that, or at the end, depending on what you want. So as I said, hacker history. If we look out to when the term hacker was firstly introduced, we need to go back to the 50s and 60s, where it was mostly tied to, let's say, a thing called phreaking, where people would take on phone systems, hack their way into it with the help of a blue box, and that's the picture you see in here in the center of the screen. And that blue box allow you to emulate phone sounds and allow you to make phone calls to somebody else. Mostly it would then involve, let's say, social engineering, convincing people to do things for you, right? And that was like, I think, the first type of hacking. The article you see on the right is something that came from a newspaper from Cambridge, Massachusetts. And it was 1963 when they first used the term of hackers. And they were just like telephone hacking, as I already said. Throughout the 90s, there's a lot of good stories about people who have used phone hacking and also social engineering on taking on stuff. One of them is, of course, known by... one of them is Kevin Mitnick, right? You've probably heard of him. He does a lot of social engineering. And the other one is also Kevin Poulsen, who used social engineering to win a Porsche car at a local radio station by manipulating it. And in the slides, I've got links to those articles, and they are really fun to read and to see how he was able to manipulate the whole contest and get away with winning that Porsche. So that was hacking, right? So if we then move on to the next thing, at some point there were mainframe computers. There were computers that were inside building offices, like helping out the businesses run, right? And I think the biggest step in that history was at some point they all got connected, right? So networks came around, people start connecting those machines to eventually the internet. And of course, what happens with something that's connected to the internet, which is widely open, that will be hacked. So one of the first tools that you could use to do hacking and vulnerability assessments was called Satan, and was created by a Dutch guy called Wietse Venema and a US guy called Dan Farmer in 1995. And the other tool that's also pretty significant for the whole like analyzing and also determining if you are able to communicate with a server was a tool called Nmap, which was created in 1997, right? The screenshot you see at the bottom here is like a scan being performed on an IP address that will then show you the TCP ports of that server that you're able to communicate to, right? So the evolution went from systems which were mostly isolated, then got connected because of the internet. And that, of course, caused a lot of problems and a lot of hacking. If we then look at the next step, that was something that happened more like at the end of the 90s, where people were talking more about security problems based on program mistakes or errors in software, right? And in 1996, the FRAC edition number 49, and you can still find it, a hacker by the name of Handel LF1 wrote his first article about buffer overflows. I believe this is not technically the first article, because the first one was written by Mudge, who also had a take on what buffer overflows was, right? So mostly it's about C programming languages taking a memory buffer and overriding data elements of it, allowing maybe eventually to execute code and so on, right? This was a problem, of course. But the other thing that also was a problem was something that was published in 1998 for the first time by a hacker called Rainforest Puppy, who talked for the first time about SQL injection. And that, of course, has to do with the fact that if you take external input within your application and let's say, or from an external input and move it into your application space, and then use it to create a SQL statement, a database statement, and you not do it in a proper way and just push it in and concatenate it, then of course that will result in dynamic SQL and of the ability to manipulate logic of queries with all consequences tied to that, right? So network connectivity, and then the hackers moved more to the application layer, right? Because those were the juicy bits that were exposed with that. And then in the early 2000s, there was the second generation of stuff happening, and I think it's mostly tied to all the worms, and also the things that products like Internet Information Server or SQL Server had to face with, right? So it was not that a single machine was being hacked by a hacker. No, somebody created a worm that will propagate itself and that would hack all the servers it came across, right? With all consequences tied to that. And code red, of course, had to do with a path variable not being properly bound, and a Unicode bug tied to it, right? And the thing you see over here, that's the request that you can use. And then eventually that resulted in execution of a shell and a compromise of the server, right? So then in the early 2000s after that, Bill Gates sent out an email to all Microsoft employees telling hey, security needs to be on top of our mind. We need to make sure that our software is secure by design and from the start, right? And I think that's definitely a big change in the whole history if we look at how software is being developed and also how Microsoft has changed the way that they develop their software. Right, so this is important, and keeping software secure, of course, all starts with the design, and our software process is becoming more complex, right? That's not a thing that helps out, because if we then look at some changes in the way that software has been written over time, we started out with the big monolith, as I said myself, like with my development career at the beginning, and then we moved to microservices, service orientation, microservices, and then at the end, right now, we probably had maybe a serverless approach, cloud native approach, where we have smaller bits of pieces like of application that we deploy on a more frequent basis with all, let's say, infrastructure as code and all additional stuff we need in order to deploy it and build it, right? And all the stuff that's being added onto it, like all the stuff we need to do in order to develop our software and release it, that's something that we call the supply chain. And what would then be a good analogy to look at as from supply chain perspective? I think the automotive industry is a good one, because we're going to talk about several problems, and they also solved some of the things already in a really good way that we also should do when we look at software development. But the car supply chain, right? At some point within a factory, there is a chassis where the car is being built, right? That's the first thing. And then across the whole chain of the car being built, pieces are being added to it, right? If you look at an average German car manufacturer, like each model will take 10,000 parts that will be added to that car. And one other thing is that most of those parts are not like, probably are not like created by the company itself, but are being created by suppliers, right? So other factories will create that part for that car that will then be put on that car. And then at the end, once the supply chain is done, it will roll off the factory plant and it will be delivered to the customer, right? So that's the whole supply chain, and each step, value will be added to the end product, which then will be sold to the customer. If we then look at software development, there's of course a similar pattern, right? So the software supply chain we're going to touch today hypothetically looks a bit like this, right? There's a developer. The developer will have, of course, code he or she needs to write, needs to put it inside the source repo. In this case, I'm using all Azure ecosystem icons, but of course, this is all interchangeable with GitLab or GitHub for that matter. The problems will still remain the same. It's just the service that I put in, which has a name, right? So it doesn't matter. Source code will be checked in, then probably packages will be fetched, right? And it will be like included within the software development with all risk tied to that. Then there is a build being executed, right? So at some point, a trigger will execute a build that will take the code, that will take the packages, that will package up everything, that will probably throw it against some test plans that will be executed, right? So in order to do the quality assurance, and then let's say hypothetically speaking, at some point there's a container image created that will be pushed to a registry, and that will then be used to, let's say, release to production, right? So maybe with all the things, but that's the hypothetically like staging things we're going to talk about. So developer source code, build, and then deployment. And if we then look at all the different aspects, let's focus on a specific part. Let's first look at the developer as a whole within the supply chain, right? This is the supply chain, and then see what types of risk are we facing. And I think the first thing, if we put on our paranoid hat, right? Because in my job, that's like one of the things you need to just look at everything and maybe be a bit paranoid in order to understand what your risks are. If we look at the development machine that we get, if we, let's say, join a company, we probably will have a new machine, a MacBook or a Windows machine that will hopefully have some good like hardware inside of it that will allow you to do a secure boot, and hopefully have a trusted platform module that will give you some guarantee of the hardware that's inside and the firmware that's installed on your machine. I'm also assuming that your machine will be maintained by the IDT department, and it will be a hardened operating system, and all the updates will be installed, right? If there's an update needed on your machine, it's done for a reason, right? And what I mean with hardening the operating system is not like putting additional stuff on that you don't need, that will introduce an additional risk on your machine. And of course, if you're like dealing with customer data or dealing with intellectual property, then it totally makes sense also to encrypt the disk in order to make sure, like, hey, if the data is at rest on my machine, then you need to have access to the decryption way of that disk in order to read that data. But then the question that we still need to ask ourselves is like, hey, but are we sure? Can we trust the hardware that's inside of our machine? And this is, of course, this is really paranoid, but this is a really nice presentation that was done by a guy called Andrew Wang, or also by his handle Bunny. And he is taking a story where he talks about how hardware can be hacked and how that's being done based on, let's say, the way that it's being produced, right? So it focuses more on supply chain hacks that are targeting specific hardware. And this is a talk that he did at Blue Hat, Israel in 2019. And he shows us that there's a really thin line between a chip, how it's being manufactured, and how it's being manipulated. And there's also, it's hard to determine if something happened or not, right? And of course, you should ask yourself, like, hey, would this something, like, this is usually something that's done on a larger scale, or maybe targeting specific users. And it's also known that in the past, hardware has been manipulated for that reason. As I said, this is a nice, intriguing story if you want to know more about hardware hacking, and he will explain how it works and how the processes are tied to that. But let's now, for us, just assume that our hardware and our machine can be trusted. The first thing then we need to do ourselves is maybe install the tools that we need in order to do our development. And I myself, I run a MacBook where I do, like, say, all my .NET research. And in order to install, let's say, GPG or OpenVPN or something, there's no real good way on doing that on a Mac, on Mac OS X. So for that reason, somebody created Homebrew, which is a package installer that you can use in order to install the dependencies that you need. And if you then go to the GitHub repo of Homebrew and then ask you, like, hey, how can I install it? Then this is the thing that they want you to do. It's like, okay, grab this shell script from GitHub and execute it on your system and throw it against your system, right? And the first question you always need to ask yourself, like, okay, can I just take a shell script that's being put on a GitHub repo for some reason and execute it on my system, probably with, I think, more than normal user rights, because you need to install something, right? Is that a good idea to do? That's the whole thing. Like, you put a lot of trust in this thing, and of course, it totally makes sense to maybe look into it and see, like, hey, what's happening here? But you also put a lot of trust in it if you just use it. If I'm installing a new package, and let's say if I need to install a new Python version, then I will probably use Homebrew to do that. And then, as I said, there's a lot of trust in that ecosystem. And if that some package gets compromised, or Homebrew itself, then that can be, that can be impactful, right? And then if people would say, like, hey, in Windows, we don't have that problem. If you do stuff with your collectly on Windows, then you're in the same space. And the funny thing that I figured out is that if you look into their website, and if you see on, like, the docs that they have published in order to install it, they already point you out, like, say, like, hey, okay, there's a PowerShell script you need to install on an administrative shell on your machine. And it would make sense if you inspect this shell script before you execute it, right? And that's totally, I think that's an honest thing to say at that point, because how do you have the guarantee that that shell script is doing the thing as it is intended to be, or has there been some manipulation happening, right? If we still put our paranoid hat on. So there are similar problems. But let's say for now, we have our hardware, our machine in place, we have installed the tools that we need. Let's now focus to an IDE and see what's happening with that. And in May of last year, some people from the GitHub security team published a piece of like, they published an article about a piece of malware that was targeting a specific IDE, a specific NetBeans IDE. And what happened is that each of the packages that were built with that NetBeans IDE got infected, and it put inside some malicious code inside of it, a dropper that will then connect to another server, I believe. It also turned out that this was a quite sophisticated targeted attack, right? Almost similar to the things that we've seen with SolarWinds, right? So somebody put effort in it to compromise that IDE and then say, hey, yeah, we can leverage it, right? So it's not completely clear who was behind it or what the motivations were, but this has a large impact if you take an IDE that's used by a lot of users. And as I said myself, I'm using VS Code a lot on my MacBook, and I love VS Code. I also love the whole vibrant ecosystem around it, and there is totally no language you cannot develop with VS Code, as far as I'm aware. At least I haven't run into one yet. There's always the extension, and it's just a quick way, and it's nice and solid, and I love it. It's minimal. But if we then look at VS Code as a whole, VS Code itself is being created based on Electron. Similar to Slack, the Slack that we're using for this conference right now, that's also based on Electron. And the site that I'm showing here in the screenshot allows you to create a dependency graph of all the packages that are used inside VS Studio Code, or at least inside Electron, right? Because you use Electron, you all use all these packages, and therefore, yeah, that might be a risk, right? And all these packages are being maintained by 110 maintainers, right? So 110 people are being will help out with creating these packages, which will eventually end up in VS Code, or in Electron and in VS Code, and even in Slack, right? For similar reasons. And it's good to build on top of something that somebody else built, right? That's the whole purpose of community-driven development. And I'm also the type of developer, like I'd rather be using something that's already been created that solves my problem in a good way than just bumping my head into it for 2 days and not getting anywhere, right? So that's the whole trade-off. But I think it's important to know that there are like 110 maintainers, but there's even a lot more contributors underneath those 110 maintainers. So just imagine if one person decides to do something differently, then what would happen, right? Electron itself also has its issues. And in 2018, there was a publication done by the fact that, hey, for some reason you can turn on the node integration again and then do eventually remote code execution, right? And that was happening with all the apps that were built on top of that Electron version. And also, as I said, VS Code itself has a lot of extensions and allows you to do a lot of things. And they also have problems, right? This is one that was published, I think it was September or August of last year, depending on which notation was used. And this turned out to be a remote code execution in one of the extensions. And then if we then look into more stuff that happened even more recently, this is one that was published yesterday, where a security researcher disclosed that he or she was able to take over the VS Code build on GitHub. And as far as I'm aware, and as far as I was able to read through it and all what's happening, right? So there's a bit disclaimer, but within the CI/CD scripts that are used for VS Code to do the nightly build, at some point there was a execute done at a shell that will do some git command. And there was one variable name which allowed the attacker to, if you were able to manipulate that variable name, allowed to do code execution and a command execution eventually, because it was an execution on the build server that was building VS Code. So the researcher figured out a way to manipulate that variable name, and then eventually was able to get a write token for the GitHub release branch of VS Code. And as a proof, he put in a text file to show the Microsoft response team of saying hey, I was able to hijack the build and put in a file. I believe he even got a nice bug bounty, right? That's a good thing if you play according to the rules. And if you publish this with Microsoft, then there's even money to make out of it. Can be a lot of fun. But I think that the key thing with this would be hey, so somebody nicely disclosed it and fixed it, allowed Microsoft to fix it. But if somebody with bad intentions was able to do exactly the same, you can probably imagine each of the installs after that package that was being built would be infected, right, in some way. So a lot of power if you're able to get your hands on tools and how they're being built. And the fact that you have these tools inside your supply chain also pulls in the supply chain of those tools into your own software supply chain because you rely on it, right? For that same reason. So a nice story, as I said, published yesterday. The link is inside the notes of the slide. So we talked about like building, like we talked about development machines, we talked about IDE tools and the way that they could be compromised, right? As we've seen with the VS Code one. Let's now focus more on the next stage where the developer decides to commit code and maybe wrap up stuff, right? That's the next step. What could possibly go wrong if we look at that step of the supply chain? First of all, the development machine itself will probably also get packages that it needs, right? Third-party libraries and so on. And I think it's unthinkable not to build on top of something that was created by somebody else, right? In order to get productivity, that's the whole power of community. But by doing that, you also need to make sure that, of course, you get the latest version, right? No vulnerable packages, and so on, and make sure that you upload those in order to not introduce any unnecessary risk into your application. Second is your machine communicates over the internet and probably will rely on TLS or transport layer security. And the whole certificate thing behind it is something that's like a root authority trust system. And in the past, we have seen problems with that. I think the biggest example would be the DigiNota case that happened in the Netherlands where one of the root CAs was compromised. To a certain degree, I would say that whole certificate root authority trust system is broken by default. And it's just hard. You cannot fully rely on it. I think that's the right thing. Similar counts to, let's say, TLS problems that we have seen over the last year. So TLS 1 and TLS 1.0, 1.1 and 1.0 had the beast and poodle attacks, right? Those are like the attacks that allow somebody to get data out of it within like padding Oracle example. Luckily, those TLS problems were, let's say, excluded from NuGet, or NuGet decided to deprecate those ciphers being used, right? And I think that's also one of the key things with the whole, let's say, communication on the internet is that for backwards compatibility, a lot of these things still need to be available, right? But that will still also have the risk tied to it. So it's good that people decide to deprecate specific ciphers if they're vulnerable to things. Another keystone of, let's say, the internet itself is, of course, domain name service, or DNS, right? So if you decide to go to a specific internet address, that will be translated into an IP address before you get there, right? That's how the internet works. And then, of course, also, if somebody puts in a rogue DNS and then responds that you need to go to someplace else instead of the internet server, then, of course, that can be a problem. Luckily, there is also some countermeasures in place by the, for example, let's say DNSSEC, which allows you to do signing of DNS entries in a whole similar way. It has, so that will be signed, and once you get a response from a DNS, you can check if that DNS, if that top level domain has got a signing key to it, and you can validate if the response was the right one. And that would allow you to see if something was a fake DNS response for that matter. But DNSSEC, for example, when I checked it for the last time, both NuGet and GitHub both do not support DNSSEC. And that's a missed opportunity in this whole story, right? It's similar for turning off those old ciphers. I would also say, like, hey, if you have DNSSEC enabled, that's an additional layer of security against hijacks of DNSs and your users maybe being redirected to another server. So let's now assume that we have the network communications and all stuff in place. Let's take it to the next thing and then see, like, okay, in order to access source code, in order to access our source repositories, we probably need to have credentials in place in order to commit code, like changes, right? And what could happen with credentials? They get compromised. And in 2019, this article was published where the Canonical GitHub account supposedly was hacked, and I believe it was just ordinary credential theft. Turning out that somebody had access to the Ubuntu source code repositories. When this article was written, there was no indication of compromise, so that something was changed. But you can probably imagine if you're able to put in code into the Ubuntu source that gets distributed across everybody who uses it, there's a lot of impact on that. I believe there were some test projects created and that's it. So the impact was minimal. And then you would say, like, okay, do big companies have the same problem? Yes. So Microsoft had similar issues, and it also probably was due to some credentials which were stolen. And I believe some private repos and internal repos of Microsoft products were being sold on the black market. So just credentials used, right? And then the first thing would say like, hey, if you have credentials, what would be a good countermeasure for you to take in order to safeguard access to a system, right? That will be, of course, using multi-factor authentication on your source repositories, right? I think that's, of course, the key thing. And that's also, if you look at, in general, if there's one thing I want you to take away from this presentation, is like use multi-factor authentication on all your accounts that you use on, let's say, services on the internet, because that makes sense to do, right? So if your username password gets compromised, then this additional factor, which let's say for this case is the Microsoft Authenticator that produces those time rotating codes, you need to have that one also, right? You want to have access, and that would have safeguarded ordinary credential theft. If you only have username password, then missing these factors would not grant somebody access, and I think that's a good thing to do. An additional thing to do would be something called GIT Commit Signing, right? So within a Git ecosystem, you're also able to, as a user, take a public-private key pair and sign every commit that you do to that Git repo. And then the nice thing is that you can then, like, if somebody looks into the history of the Git repo, they can see you're verified, meaning that it's a public-private key pair that was put into this project and that was like recognized as being one of the contributors of this, maintainers of this project, right? So even if somebody steals your username, password, and even your multi-factor authentication keys, like is able to produce that, then this would still be an indication of compromise if somebody would always use verified, like signing commits, and one commit doesn't have it, right? There can be an alarm bell saying like, hey, this is not looking right, there's something wrong, or we need to check out what's happening. So Git commit signing can be an additional layer of protection that you can use. And I already touched it a bit, right? Because if we develop software, we normally always use third-party libraries. And by pulling in third-party libraries, you also pull in the supply chain tied to that third-party library. And if there is a security problem, a vulnerability, or maybe even a compromise, then it can have issues. And this is the thing that happened in 2018, where a event stream package within NPM's ecosystem was compromised. And it turned out to have a 2 million weekly download. And event stream itself was quite minimal. It didn't do much. And I believe it was pretty stale, and there was not much active development done. And somebody decided to contribute to the package, and then at some point was able to become maintainer, and then decided to publish a package that was malicious, that had some code injected to it that would target specific Bitcoin wallets. I don't think the person was pretty successful with the hack, but you can see, like, if you have some intermediary package within the whole, like, transitive dependency tree, right? The one you saw just before VS Code. You can see the impact you have, right? And because it was used by 2,000 other packages, I believe those were the figures tied to this one, it would cause problems. So if the third-party library is compromised and that third-party library is in your software, then your software supply chain is also compromised. So let us move on to the next stage. Let's say, okay, we have done the thing that we do with our code. We have taken all the libraries. We know that it's right. Now we're going to build our software in order to do the last step before we can release it. And if we then look at build and deployment, then what could possibly go wrong? And then we can do a little bit step backwards to the stuff that we talked about with the development machine itself, right? If you run, let's say, self-hosted agents to build your software, then of course you own the hardware, and then the same question arises like, hey, can we trust that machine and the hardware that's inside of it? Or similarly, if we rely on a cloud vendor to give us the build agents, then we put a lot of trust in that vendor, right? And don't get me wrong, I do think that every cloud vendor probably does the best he or she can in order to make sure that those build agents are being updated in the best way, right? There's power of the fact that it's done for everybody all at once, right? I think that's a good thing. But of course, you still put some trust in that. Similar counts with all communications done, right? TLS still is an issue in this thing. And what about Docker images or layers of Docker images that get compromised? The thing that amazed me when I did initial research on this slide deck was that even if you have Docker Hub, and if you publish the image to, like, your images, your container images to Docker Hub, there is no such thing as two-factor authentication for Docker Hub. And it was turned on, and I believe it was turned on in a beta when I was looking into it. I didn't check into it like before this presentation. I should have done this, but I think that's a missed opportunity, right? Similar to the things that we've seen with the code. And of course, if you have a build server yourself, then the build server can be compromised if it's one that's being self-hosted, right, on your own infrastructure and so on. A small sidestep would be something that happened to Twilio in July of last year. So one of their SDKs that they create was compromised, and that was compromised in a way that at some point the build was taking files from a specific S3 bucket and put that inside of the release package. And it turned out that that S3 bucket wasn't properly locked down, and somebody was able to put different files into that S3 bucket. I believe they were like pretty quickly acting on it, and they recognized it quickly, so that's a good thing. But as I said, like, because the software build process itself has become more complex and just took some files from a specific location someplace else, that's a problem, right? And there's a nice write-up in this blog post where they explain exactly what happened. Similar to something that happened to Webmin, and I think it was 2019. This was published at the AppSec Village at DEF CON in Las Vegas of 2019. Turned out that one of their hosted build servers of the Webmin tool was compromised, and was compromised for, I think, a pretty long time, almost a year, I believe. And what it did is that it planted a backdoor in each of the binaries that was created, right? And nobody, at least did recognize that. And at some point, they did see that, and they had like a series of releases that were affected. It was a backdoor, and I'm not sure how effective it was, but yeah, because the build server, the hosted build server, was compromised and the server was used all over again, that was of course causing a problem. And I think similar things are applicable to what we have seen with SolarWinds, right? So this is a really nice blog post that was created by CrowdStrike, where they explain how the build process of one of the SolarWinds products was compromised. And don't get me wrong, this as a whole is a sophisticated supply chain attack, because it has a lot more moving parts inside of it, right? And a lot more happened because there was a piece of malware that infected the build server that eventually recognized MS Build being executed, and what it then did at the end, it took a file, a specific source file, and it replaced it with its own version, right? And looking at the solutions that we're going to come up later on in this presentation, I think there's a way to fix that. I think there's a way to recognize that. But don't get me wrong, it's not the fix for SolarWinds as a whole, because there was a lot more stuff that went wrong, right? And also, if you look at the impact it had on all the different other companies that were hacked based on the fact that this SolarWinds product was hacked, yeah, it's a really big story. But this, as I said, this blog post exactly explains what's happening, and we're going to focus on later on in the demo. I'm going to show you like how they could have recognized this happening. So as I looked into all the stuff that we see in this slide, right? All the parts within the software supply chain, and probably some of the countermeasures I already talked about a bit. Those are all pinpointing, let's say, specific countermeasures for that area, right? Signing or Git commit signing will only help you on your source code, right? But there's no guarantee that the source that's being developed by a developer is also the source that ends up in the product that will be deployed or that will be released to the customers, right? There is a big gap between that. And with all the things I've shown, they will only fix that problem on that specific area, but not the software supply chain as a whole. And that's still a problem. And how can we move forward, and how can we fix that kind of a problem? I think the key first would be to be more able to do reproducible builds, and reproducible or deterministic builds, meaning that, let's say if you use a library on the internet that has source code published because it's open source, right? You should be able to grab that source code and build the binary, the library, in the same way as you would consume it from it, because otherwise, how can you compare what's inside of it, right? How can you even say like, hey, this is the source code, these are the binaries that are being produced out of that. How do I have the guarantee that that's really the thing that's inside? And reproducible deterministic builds should give you some guarantee of that, right? So given the same source code and build environment, it should produce the same output, allowing you to verify like, hey, yes, this is the library and this is the source code that was used to build that. If we look at .NET as a whole, since Roslyn 1.1, there is some kind of determinism inside of the build process itself and how items are emitted. And if you look into the GitHub repo design document that I put inside the notes, they state that given the same inputs, the compiled output will always be deterministic and will always be the same. And there's a list of inputs that they define. So it's not only source files, but it also means the installed SDKs, the installed software, that kind of things, right? Maybe some other tools that you use inside your SDK, they will all influence the way that eventually the classes might be emitted. And that's the key. These inputs can be found, as I said, in the compiler docs, but if you look at it right now, and if you would start out a console app, you can definitely do exactly the same, excluding maybe some PDB and some other files that are being put out that might change the binary, right? Because you want to be able to compare the binary bit by bit. It should be exactly the same, and that makes it hard to compare. So looking at that, saying like, hey, deterministic builds, would that then be sufficient? I think we need to step back a bit and then look at the automotive industry once more in order to see the additional things we need to do in order to secure our supply chain. So I think we all have been in a spot where we got a recall from our car manufacturer or maybe our dealership saying like, hey, you need to bring back your car because there's a problem with, let's say, the seatbelt, and we need to replace that part. There's some faults in it, and yeah, but just for your safety, you want to replace it, right? And for some reason, car manufacturers are able to determine that you have got that piece of faulty seatbelt, let's say one of the parts inside your car. And of course, the car, as I said, would consist of a lot of different parts from different manufacturers, right? So how would they hypothetically like solve this problem? And I think the key can be captured in this. If we look at this, this is, let's say, if we focus on disc brakes that are being put on a car, like how would that look from automotive industry perspective? At some point, we will take iron ore that will be then used to produce iron, right? And that will be done in a specific factory. That can be the Taylor Steel factory. That's one based in the Netherlands. Let's say then that steel would then be tested according to standards, ISO standards, and then that steel will be batch numbered and then distributed across all like plants that will use that to create their own products from. Let's say Bosch is producing disc brakes, and they will use that steel batch that's identified with that number. They will then produce the disc brakes. They will also do their own certification, their own testing that they need. They will put a serial number on it saying like, hey, this is this series of products. And then they will probably distribute it to all the car brands that will use that similar disc brake on all the different cars that they build. Then at some point, that disc brake will be put on a car, right, within a plant. And there will also be an exhaust being added to the same car, right? There's tires. And at the end, of course, that's all being put to a car that can be identified with a vehicle identification number. And that's, of course, the whole administration that a car manufacturer need in order to keep track of the stuff that's inside. So let's say for some reason the Taylor Steel factory figured out like, hey, the batch that we produced had some faults in it and it might break after X amount of time. Then they can push to Bosch saying like, hey, this batch had some problems. You should figure out what you need to do with it. And then if they then decided like, hey, we need to replace the disc brakes of the cars that have these disc brakes on, then that can be done, right? That's the next step. So there's like a whole book there's a ledger almost of stuff that's inside that car. And that makes it traceable for them. And that allows them to guarantee your safety and have that part replaced before something bad happens. And I think if we look at software, there is a need for a similar thing. And Microsoft, Google, and all the big, like say, software companies have recognized that there is a need for these types of standards. And one standard can be called the Software Bill of Materials, which is an industry standard for describing software. You can see it as similar to, let's say, if you buy a product in the supermarket, there's a label on it, then it will explain to you what's inside, right? I think for software and for libraries, we want to have similar things. Who created it? What's the product? Do we have a guarantee if the product is altered or not, right? How was the product created? Which source code was used? Maybe also what type of quality assurance was done, right, in that thing. So that there are different answers. There's different stuff you can put inside the software bill of material, and it's of course quite abstract. Cyclone DX is a project that's being run, and it's a lightweight SBOM, which allows you to produce a dependency graph of the projects that you're creating. And I think they have plugins for all different stacks, like .NET, Java, JavaScript. They're all around. And it allows you to create a transitive dependency graph, right? So all dependencies that you use inside your software, and also all transitive ones. So if at some point you get hold of the fact that some library that you've used in the past has got a problem, like a CVE has been published, and there's a security issue, then with that SBOM, you're able to validate, saying like, hey, this product uses that library, so we should take action of maybe making sure that the next version has got a new one in, because it might not be a risk, or it's a real big problem, we need to fix it right away, kind of thing, right? NTIA is an organization within the US who also does a lot of SBOM standards, and they have got like a lot of different documents. And if you're interested in, please go to their site to figure out the documents and the papers that they created. And there's still a lot of working groups that are working on software bill of materials, because as I said, it's still a piece of abstract right now, but we need to make sure that it matures and it's usable for everybody. So there's still a footnote I had to remove of this slide, but it's not that confidential as it states right now. But there's one tool that really has a nice approach on securing the software supply chain, and that's a tool called In-Toto. And I think it was people from University of New York and New Jersey teamed up, and they created In-Toto tool, and that allows you to secure a software supply chain in a better way. And this is the demo part, and I'm briefly going to just talk you through a bit of what the terminology is that I'm going to use. So we want to capture the software process as a whole. And in each of the process, there are different functionaries. And functionaries are people that are participating in the software supply chain, right? So there's myself, a project owner, there's a developer involved who does the development work, and there's a dedicated guy that does the packaging of the application, right? So each of these steps can be written down, and me as a project owner, I will create a software supply chain. And this system relies on public-private key cryptography, and it will sign things, right? So each of the functionaries will be having a private key that they will hold to themselves, and there's a public key that will validate. So we will see in the demo later on, the developer, she does her work, she will check in source code, she will sign it with her key, and then the packager will pick it on. But because we have a supply chain that I as a product owner have defined, we will describe what will happen by who, and what will be the materials and byproducts, right? So what will be the produced output. And the nice thing is that materials are input and products are output, but they can also be used as materials from other steps, right? So if we describe our software process, and I will show you a layout in the demo, we can chain up things, and I think that's the power. That's the power of this. So let me move to my VS Code, and this is a demo that's inside of the GitHub repo that also contains the slides. So don't worry about grabbing hold of this. So the first thing that we need to do is that we need to, myself as the owner, we need to make sure that we create the layout of the supply chain. And there's a lot of code in this, but let me just briefly describe what it does. So I will create all the steps that needed, right? So at some point, the developer will start out the project, will produce source files. And each of the steps, we will define what the materials and products are. And each of the steps will also be chained to each other, right? So the developer will check in work, then the packager will publish that, then that publish will then be packaged. And that's something that we can then validate. This is the whole layout. And this script will just execute it, and it will take the public keys, it will put them in the right place. So I'm just going to execute that and then produce the layout. So there's a layout file right now being created, which contains it all. It has the key, the signing, it will have materials that it expects, and all the description of the source and of the materials and the output that is being produced. So we need to have the layout itself, and we need to have it for our final product in order to verify. And we also need to take my public key, because I took the private key. I'm the owner of the product, and I will sign the supply chain saying like, hey, these are the steps. This is the testing that we do. We do the packaging like this. Maybe the other tools like linters are being run. There's a lot more stuff that you can configure inside your supply chain that needs to be part. And each of the steps will produce rubber stamping artifacts, which are called link files. And those link files can then be validated later on. So let's say right now the developer decides to do our work, and I just put in a script that will do all the work for me, because you always fail at typing. But if we then look into the create script that's being used by the developer, we will just say like, hey, okay, for in-toto, we start a step, and it's all being signed by the developer in this case. And we're just going to do the ordinary thing like, hey, do a new console application. And we create the products, which is this source file, and that will be signed, right? So pretty straightforward. And if we then look into it, there's a link file created, and that's the output. So let's safeguard the link file, saying that's the step that's being done. I put it inside the final product folder. And now we're going to move the app folder to the packager, right? So let's say packager checks out the source code, grabs the branch he wants to work on. I'm just going to move for demo purposes to make it easier for myself. So now we're ending. We're looking at what the packager is going to do. First, he will do a publish, which of course is still a step that will do a publish of the app itself to a folder. And then he has a package script that will also package it up and create a tar file that we can then use. So if we then look into the directory itself, there's like 2 link files being produced for each of the steps. So let us copy those files to the final product folder, because we need to get everything in place, right? All the artifacts of each of the steps. And we also want to make sure that we take the end product, which is a gzip tar that will have the product itself. So let me maximize this one a bit. And now we're going to go to final product. No, final, we're already in the directory, final product. And now we're going to say to in-toto, please verify this. And let me grab the one from my history. So we're going to say, okay, we've got the artifacts all in place. This is the the layout file. This is the public key file from the owner that's being used, and show us what's happening. So there's a lot of steps, right? It's still a bit verbose, but at the end we will see like, hey, the software product has passed our verification. So the software supply chain, the development, the packaging, the publishing, the packaging has all been done according to the steps that are normal. So let's say at some point somebody decides to hack it, right? So this will be the SolarWinds case where somebody decides to take the product and manipulate it. So let's say for some reason the packager decided to change the source file and decided to, hey, this is the source file, and let me say hello NDC London or NDC London, and save that file. Right, so source file has been manipulated and has not been the same, similar to what the build process would have done with the MS build one that was infected by the malware with the SolarWinds case. So right now, if we then go to Naut again, the function, the packager, and then say, okay, he's publishing the app again, and we're packaging the app again for the same reason. And then we're gonna take all the link files because we need to gather those, and we're also gonna take the output again. And if we now say final product, then we can still do the same. Let me maximize this once more and clear out. So now we can say in-toto verify, and then do the same. And if we then run, then at some point it will say, hey, it has failed. And this is the root verification that's done. And for some reason, it says like, hey, so within the whole chain, at some point, the source file was altered, and I didn't expect that. And that's the whole like capture of this, right? So the supply chain itself has been described. There is a signing being done, and that allows you to validate that. So I think a pretty powerful concept. And it would have helped SolarWinds. It would have allowed you to recognize that fault and manipulation. DataDog uses In-Toto in a heavy way, right? Because you can see like it's still, there's also still big portions academia on In-Toto and the stuff that you see. But they've used it inside their builds for their agents, which is a nice read if you want to read more about it. And if you use the Google Cloud Platform, Grapheus and Cretis also already incorporate that. So Grapheus allows you to gather that data, right? Gather those link files, gather the artifacts. And Cretis is something that then allows you to do the decision making if you want to deploy that Docker image to your cluster or not. And that's the powerful thing. And you can achieve similar things with the Azure Pipelines artifact policy. Right now, it only supports checking for, let's say, hey, this Docker image, make sure that only this port is being exposed, that you can connect to it, those types of things. And I can definitely see a place for, let's say, In-Toto artifacts being consumed by the same policy checks, and then also allow you to take decisions. Another thing that's also a possible approach of fixing the whole SolarWinds process would be a tool called Gitian, and I'm not sure, I didn't put the link in, but Gitian allows you to also reproduce build environments in the same way, and it can be used to do 3 builds of the same product and then do it across, let's say, several systems, and then check if all the artifacts that are being produced do match, right? So if there is a build server compromise at some point, then you also have a tripwire that will alarm, let's say, if something happens that you don't expect. So I think we're also getting close to the end, so I want to wrap up. I think it's the key thing that I want you to take away from this presentation is that you need to be aware of your own software supply chain and stuff that you're doing, but also the things that you pull into your own supply chain, by the packages, by the tools, by relying on the hardware, by all the stuff that we've seen, right? So knowing what you're consuming and pulling into your products itself. Please use multi-factor authentication on all your accounts. And also, of course, it's important to integrate security into your development lifecycle. So best code practices, static analysis, third-party library analysis, it's all important, right, in this whole thing. And on top of that, the best practices, and learn more about the software bill of materials. I think that will be the next step, because there's definitely a lot of things that need to be done right now, but we're moving into the right direction. And yeah, I'm confident that we're able to not fully tackle this problem, but at least have enough indicators to act on, right? And I think that's the key. So with that said, I'm going to say thank you for your time. I hope you enjoyed the presentation. If there's any questions, shout out in the chat on the WebEx right now, or put them in the Slack channel. You can also find me on Twitter with my handle, or send me an email. And I'm going to be around, of course, for the next days. And hope you enjoy the rest of the conference, and see you next time.